In this video, we are going to examine different algorithms for multiplication and different ways to model multiplication. It's really all about, can we visualize what's happening when we are doing multiplication? It's not just a process, it's not just steps, but can we see what's actually happening? If you have your base 10 pieces, I recommend you get those out for some of the activities that we're going to do here, some of the questions. So these base 10 pieces, right, there are so many different suitable models for illustrating multiplication, and we're going to look at how we do that with our base 10 pieces. And so what we're going to do for this first one is look at the multiplication problem 3 times 145. 3 times 145. And so all I want you to do is think back to the exercise we did in the previous video with the base 5 pieces and see if you can do this problem using the base 10 manipulatives, where you lay those out and do some regrouping, multiply by 3, do some regrouping using the minimal collection. So I want you to pause and try that first with those base 10 pieces. So if you've done that and you're now coming back here, what you probably started with was a grouping that looked like this, right? There's our 145. And then you got out 3 of those, right? You just took 3 of those same groups and then you lay them out and they look something like this, right? So we had the same grouping as here, but then we just repeated it 3 times. Again, there's that idea of repeated multiplication, okay? So the next thing that we're going to do is we're going to regroup these, right? We're going to regroup them so that we can have that minimal collection. And when you regroup these, they turn into something that looks like this. What we end up with are 4 of those flats, which are all 10 by 10s. We end up with 3 of the longs, which are 1 by 10s, and 5 of the unit pieces, okay? So now what we're going to do is examine this same problem with our traditional multiplication algorithm, our normal pencil and paper algorithm for computing this. We would say 145 times 3, right? This is what we would do. And then as I go through this, see if you can connect that to what you did with your manipulatives. So what would we do? 5 times 3 is 15, and we would write 15, and we would carry the 1. Think about what that looks like in terms of your base 10 pieces. Then we would do, so first we did this, now we'll do 3 times 4, which is 12, and we would add the 1, which is 13, and we would put our 3 down here and carry the 1. And then we would do the next piece. 3 times 1 is 3, plus 1 is 4. So does this number here match what we have over here? Well, if we column these off, these are the units, these are the longs, and these are the flats. So we have 5 units. 1, 2, 3, 4, 5. We have 3 longs. 1, 2, 3, and we have 4 flats. 1, 2, 3, and 4. And so did you consider how the regrouping occurred when we did this, right? What were we actually doing? When you first lay these out, what you ended up with were all of these unit pieces right here. And there were 15 of those unit pieces, correct? What you eventually did was you sort of minimized those. You said, all right, I only need to end up with 5 of those here because the 10 can be regrouped as a single extra long piece. And then you did the same thing with the longs. You looked at the long pieces and you said, well, we've got 4, 8, 12 of those, plus this 13th one over here. And you did another regrouping. you only ended up with three of the longs here and here. That's this number in that longs column, the tens column. And you regroup them as one additional flat piece. And that's how we ended up with four of them here and four of them here. So again, when you start to build these ideas of regrouping, it helps lay that foundation for understanding our place values and how this algorithm that we are familiar with, how that works. And that is incredibly important. Another thing that's really important for everyone, students, young students especially, to understand is the idea of multiplication by 10. Multiplication by 10. We know that when we take a number like 5 and multiply by 10, it becomes 50. But why is that? So what we're going to do is look at a model using, again, the base 10s, manipulative. So if you want to do this, you can follow right along with that. So the question is, why do we just sort of add a 0 here? Why does that work, right? We started with 5, we just stick a 0 after it when we multiply by 10. And so here's a nice diagram with the manipulatives for if we were going to say multiply the number 34 times 10. And so even if you want to explore this on your own using manipulatives, maybe sketch something out, see if you can sort of make sense of why we just end up putting a 0 at the end of 34. Because the real question that we want people to understand is, why do we do things the way we do? So here's what the manipulatives would look like if we arrange those. So let me expand this on the screen here. So let's examine this. What we see here are so the 3, right? The 3, that's in the tens column, right? That's represented by 1, 2, 3 of these long pieces. Well, what happens when we multiply those by 10? Imagine I took this and I just laid it flat here, right? I took that long piece and I laid each of them across the top. When we multiply by 10, what we are doing is we're taking each one of those and we're laying them out 10 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 times. And we do that 3 times, right? So what we end up with is 3 of these 10 by 10s. So this is now a 10 by 10. This is now a 10 by 10. And this is now a 10 by 10. And how many do we have? 3 of them. Each one of these long pieces got extended by a 10 and turned into a flat, right? So it's kind of like they all move up a level into the next size of those arrays, the next size of those rectangular arrays. If you start to examine our traditional algorithm, 34 by 10, the 3 from the longs right here moved over to here. It moved from the tens column into the hundreds column, and this shows why. Then let's explore the 4, right? This was the number 4. This was in our ones or our units space, right? So the number 4 was here. So we had 1, 2, 3, 4. Imagine each one of those at the top. And then we multiply it by 10, which drops it down all the way. Now we've got 10 of those. 10, 10, 10, 10. Instead of 1, 1, 1, 1, we now have 10, 10, 10, 10, right? And that's 1 times 10, another 1 times 10, another 1 times 10, another 1 times 10, all grouped together to be 40, right? So this entire group turns in from 4 to 40, and it shifts over a column. It goes from the units place to the longs place, from the ones place to the tens place. And so that's this idea that you can start to explore, but why is it that we just end up adding a 0? It's really because our 3 and our 4, right, which were here, they both shifted over a singular place value. They both got 10 times bigger than they were. And so what we end up with is 0 ones anymore. We don't have any individual units, right? So we represent that with our 0. So I think that's a fun one for you to explore and really examine to understand why. When we were doing addition, we talked about the idea of partial sums. And so now what we're going to do is explore the idea of partial products. So partial products, it's kind of like the different sub-steps as you work through a traditional multiplication algorithm. Again, we're going to sort of move on from our base 10 blocks because once you get to 2-digit numbers, say 18 times 23, that becomes a little tricky to do with base 10 blocks. It gets a little bit impractical because the size of the numbers increase so big. If we were going to do this, we would have to represent the number 23 18 times, right? 23 plus 23 plus 23 with base 10 blocks, right? We would have to do this 18 times, and that becomes a little impractical. So once we start to do 2-digit numbers, then we start to move into the idea of rectangular arrays, okay? And we're going to use rectangular arrays to illustrate this idea of partial products. And so what I'm going to do is show you what the rectangular array of 18 by 23 would look like. So here's what that array would look like. And we're going to examine a couple things. So the first thing is that we have the number 23 represented across the top here, right? There are 23 of these individual unit blocks going across the top. And as we look downward from top to bottom, you'll see that there are 18 of these rows. So if we first start to link that to the idea of repeated addition, here is a row of 23, and we would repeat that 18 times from top to bottom. 23 plus 23 plus 23, etc. And you can see how that would be a little complex to do. So that's why we start to use these arrays. And what you'll notice is I've got these segmented off with these big bold black lines. So what do you start to notice? Well, this is a group of 10, and this is a group of 10. And so in this square, we have 100. This is another group of 10 and a group of 10. So this is also a group of 100, right? So there's our base 10 flat pieces. Over here on the far right, what we end up with is 3 times 10. And so we get a group of 30 there. If we look down here, we still have 10 going across, but we only have 8 left on this section. So 8 times 10 is 80. We have the same thing here, 10 and 8 is another 80. And down here at the very bottom, we have 8 by only 3, which is 24. And so now if we've broken it up into 6 different little segments, and if we add up all of the numbers that we have in here, we will find that the total number of these individual little small squares, we add up all of these numbers inside, is 414. So what I want you to do now is, now that we know what our product is, take a peek at what you think it would look like if we did our traditional multiplication algorithm the long way, and how that starts to relate to these different segments on the inside of the array. So maybe just go ahead and do that. Try doing 23 by 18 the long way, and then see how that starts to connect with the numbers inside here. So what you might have seen when you did this was 8 times 3 is 24. Here's the 4. Here's the 2. And actually what I'm going to do that a little bit differently. I'm not going to write the 2 up here. I'm going to write it right there. Okay? That's the number 24. And then I'm going to do 8 times 2, which is 16. And I'm going to write the number 16, but it's really not times 2, it's times 20. So really that's going to be 8 times 20, which is 160. Okay? So pause right there and notice something. 24 is represented with these blocks right there. And 160 is represented with all of these blocks right here. These are the first 2 partial products. Here's a partial product. Here's another one, right? We do multiplication and then we do multiplication again. 8 times 3 and 8 times 20. It's important we know that that 2 represents 20. Let's keep going and let's do the same thing with the 1. 1 times 3 is 3, but that 1 is in the tens place. So really this is 10 times 3, which is 30. And then we do 1 times 2, which is 2, but think about where it is for place values. This is 10 times 20, which is 200. Let's do the same thing we did before. 30 is represented here, and 200 here is represented here. So what we end up with, again, are 2 more partial products. Again, partial products are each individual step of multiplication. When you do a 2-digit number times a 2-digit number, what you end up with are 4 of these partial products, right? And then we add them, right? So we're adding each of these numbers here, but they're even grouped a little bit differently. The 80 is grouped into 160. The 100s are grouped into 200, okay? Because we're doing, again, 20 by 10 as this step there. So you're starting to link our traditional algorithm with these arrays and how these things that end up getting grouped the way they do. Again, we end up with 414. So now I want you to try one on your own. I want you to take this. I want you to imagine 13 by 17. I want you to sketch, right? So draw out, sketch what a rectangular array would look like for 13 by 17. Then write down the paper and pencil algorithm for it with those 4 partial products. And then just start to consider the connections again between the diagram and your paper and pencil algorithm. Okay, so take a few minutes to sketch that out, do the algorithm, and then come back to the video. So what you probably did was something that looked like this. So let's examine this. Let's examine these pictures again. 13 times 17, your partial products should have been 21 from doing 3 times 7, 30 from doing 3 times 10, 70 from doing 10 times 70 or 10 times 7, and 100 from doing 10 times 10, right? So these partial products are shown with the 4 different ways we do multiplication in our traditional algorithm. Then we link these to the different segments, okay? So 3 times 7, 21. Where do we find that? We find that down here. 3 times 10 is 30. Where do we find that? We find that here. 10 times 7, again, that's this 7 times this 10, okay? These segments, 10 times 7. And then lastly, 10 times 10, this 10 times this 10 is this segment in there. When we add all those numbers together, we end up with 221. Sometimes it can help to even draw these little arrows so you can see where they come from. Again, 3 times 7, that is this segment down here, okay? So you can connect each of these segments to one of the partial products. So again, partial products and understanding how those different arrays are connected to those partial products is crucial. Try more of these on your own if you're really curious and want to explore this concept more.